Hi, Jennifer. Hey, Dimon, this isn't for you, alright? We're gonna learn this in AP Physics like next week, alright? Hey, Alex. Hey, Lexi. Hey, Rosie. Naya, long time no see, girl. Where have you been? Huh? Not Naya. Where have you been? Huh? Good to see you. Well, good morning, Tim. Good morning, Alex. Um, John. Well, Naya, I hope. I mean, if it's too private, you don't have to answer. But like, are you feeling better and stuff? I hope you are. Hey, John. Hey, Ethan. So, guys, I'm a little upset right now. You want me to tell you why I'm upset? Hey, Laura. Jennifer, let me tell you. All right. So yesterday, today is the 4 p.m. the administration of the AP exam for AP Physics 1. And even though I don't think the AP exams this year are that valid and stuff, most students are still going ahead and taking them. And they're taking them with like the normal amount of stress that comes with them. Like, I told all my students not to worry. Everyone's worrying anyway. It's fine. But what that means is like there's like this huge scramble to cram and study and help prepare as much as you can for the test. So I made a review video about like momentum and collisions for my AP students yesterday. And it's on YouTube. And today I got a notification that I got a couple comments on the video. And I checked, and even though I only have 34 students in my AP Physics class, there's like 250 views on the video. So I guess like the whole scramble to study is not unique to students in my class, right? So I feel like a lot of other students are, just trying to find resources and they're watching the video. A lot of students like outside of our school. There are two comments on there, and they really pissed me off. Right? One of them is like, I mean, in and in itself, it's fine. It's like, oh, this is great, thank you so much. And then they commented on my physical appearance that made me feel very uncomfortable. The other comment, get a load of this, kiddos. You ready for this? This one kid said, get an on-person microphone for your audio quality, dude. Other than that, thanks for helping me out. I know I shouldn't get upset, but get an on-quality mic for your audio quality, dude. Dude? That's what I'm saying. like, you little punk, you think I'm making this video for you? You think I'm gonna spend like $400 of my money just so you can have better audio quality? Who do you think you are? Like, you're fucking welcome, kiddo. Like, ugh. Whatever. Dude. I bet he goes to Sty. Okay, but let's go over the homework, right? Cool. So basically, beat frequencies occur. No, it actually isn't. Like, I've watched some of my videos just to see, like, just to get it from the student perspective, right? Of like what it would sound like from your computers at home and stuff, because that's what any teacher should do, right? You should like try to imagine what it's like for your students, and it's definitely like nowhere near the audio quality that I want. But I mean, I'm not gonna spend money on a mic, right? Like, I'm already spending money on this, on these. Like, come on. I'm on a teacher salary here. I'm not a YouTube superstar yet. Although, ironically, people like him are helping me reach that, right? Once I hit my 1,000 subscriber count, I'll do a what reveal should I do, guy? I have no idea. Okay. Good morning, Cassie. Good morning, Shelly. Good morning, Josephine. Okay, yeah. 1,000 subs. I will reveal my. I have no idea. I feel like you've already seen my apartment, so. I have no idea. Anyways, let's get started. Okay, yeah, face reveal. Face reveal at 1,000 subs. Okay, guys, hold on. Okay, so face reveal at 1,000 subs. Okay. Let's get started with physics. Okay. So I want to take around like 5 minutes to go over the homework. Okay. Because I think it's its own kind of standalone topic, but I think it's like pretty cool with like how music goes and stuff. All right. So I can have waves that look like this, and then waves that look like this. That's not gonna like give you a very interesting result when you combine them. But if perchance, like instead of this wave as a second wave, you get a wave that's very close in frequency to that. Like, what happens when I combine them, right? If I combine them, you get a wave that kind of looks like this, okay? And I'm gonna make the frequency of the green wave a little smaller, so its wavelength will be just a little bigger, okay? Okay? So what I've done here is you can see that there are areas of constructive interference and areas of destructive interference, right? So there's destructive interference here, there's constructive interference here, constructive, destructive, right? So what the superposition of this wave looks like, right, is it's going to be, right? Because basically you're going to have areas with constructive interference that make it really big, areas of constructive interference that make it very big, Areas of the next constructive interference happens here toward it. But then you have areas of destructive interference, and they basically go to 0, right? That's what the beats are, right? So when you turned on the 2 different frequencies and you heard periods of silence, like that's what these are. And when you heard it get a little louder, that's what those were, right? And of course, like when the frequencies match up perfectly, right, like this, it's always constructive, right? So you're always going to hear like a really clean, crisp note, and it's like not going to be a problem, okay? And what you should have heard and what you should have discovered like along the activity was that the frequency of the beats, which is like the periods of silence, right, is just equal to the frequency of one note minus the frequency of the other note, right? So when you guys played a frequency of 440 and 441, you should have heard 1 beat per second. And when you put a frequency of like 442 versus 440, then that would have given you a beat frequency of like 2 beats per second, like wah, 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 right? Yeah, and the way harmony in music is formed is sometimes, right, like your beat frequency has a very special like harmonic relationship with like your first and your second frequency, and then you get like really cool chords and harmonies, right? If you play like a major third, it sounds really good. That's because like the interference pattern between those 2 frequencies is going to sound pretty cool, right? That's another thing, you guys, I welcome you to do in your, if you're going to play around with multiple tone generators, you can actually look up what frequencies correspond with which notes. And if you want to play like a chord, for example, it's like, oh, I want to play like an A and a C sharp. That'll give you a major third. All you got to do is look up what frequencies those are and then plug them into your tone generator, and you can like create like little baby music, you know? Okay. Oh my gosh, 23 viewers. Wow, we're back up to week 1. We're back up to week 1 viewership. All right, I think that's cause enough for a face reveal because this mask is super uncomfortable. Can I get some whoas in the chat? Whoa, it's his face! Holy moly! Okay, so that's like a really basic review of like the homework assignment from yesterday. Oh, we're on our last sheet. Uh-oh. I guess I gotta buy more paper instead of a on-person mic. What a punk. What a punk. You know, it's just the tone. It's the tone with which he asked. It's not just that he called me dude. It wasn't even a suggestion. He used the imperative tense. And for those of you guys who aren't really paying attention in English class, the imperative tense is like the command form of the verb, right? He didn't say, you should get a mic. Or it's like, it might be better to get a mic. He's just like, get a better mic, dude. I'm telling you, man, the internet brings out the worst in humanity. You know, I'm pretty sure if that kid met me face to face, he wouldn't have said it like that, right? It's just like, and that goes to a lesson to you guys. You know, when you're writing emails, when you're like posting a comment on social media or like whatever, like, you know, just be aware of your tone, right? And try to pretend like the person is really there, right? We can't afford to lose our humanity, you know, in this new digital age. You know? Anyways, let's go over one of my favorite topics in physics, all right? Resonance. Oh, for this I need two objects. I gotta check if this works for a second. Hold on. Oh, it does work. Okay, so the first thing we gotta go over is a definition called natural frequency. And I'm going to define natural frequency as the frequency an object vibrates at when agitated, right? Now, there are many different ways to agitate an object, right? So the most simple way to agitate an object is just to hit it. So I have this wine glass here, and I'm going to hit it. You hear that? Oh, it's a C, but it's a little out of tune, but whatever. It's okay that it's out of tune because this isn't a tuning fork. It's just a normal object that happens to resonate at C, right? So its natural frequency is that, right? So, and it's vibrating at that frequency because I agitated it, because I hit it. But there's another way to agitate it, right? Some of you know this trick, but if you wet your finger a little bit and rub the top of the glass in a really specific way, right? Hold on, wait. Hold on. It's been a while since I've done this. A year, actually. It's not working. Wait a second. Oh, what the heck? I've lost my talent. Okay, hold up. That should help it. Okay, so let's try this again. You don't need water. Sometimes some glasses you need water, so I just poured water in here. There we go. Oh. So that's the other way to agitate it. So I can like rub it here, or I can just flick it there, right? It's always going to play the note. And that's its natural frequency. Everything has a natural frequency, right? It's not just a glass. Like, unfortunately, like if I hit like a table or something, its natural frequency is like a little muddled and weird. But it's not just for sound. Okay, so let me give you an example. Like if I have, for example, a pendulum, okay, it also has a natural frequency. Okay, what is that natural frequency? Let's find out, right? So hashtag wrong science, right? What is this pendulum's natural frequency? Ba, 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 right? So no matter what I do to it, it's always going to oscillate at this natural frequency, right? How do I change it if I like change the length? Now it's ba, 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 ba. So this is almost 1 hertz. I'm trying to adjust it so it's just 1 hertz. One Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, right? So this is a pendulum with a natural frequency of 1 hertz, right? I'm not sure why that happened. It's probably due to my terrible microphone, right, Josephine? So what I'm saying is, so everything has a natural frequency. Like a pendulum has a natural frequency, because as soon as I hit it, right, It's now going at its natural frequency, right? There's nothing I can do to make it vibrate at another frequency. It's always just going to vibrate at this frequency, right? So this is like exactly what happens, like super slow motion to this wine glass when I hit it. Like you can't see really well, but when I hit it, now it's vibrating super back and forth, like 256 times per second. Why do I know that? Because a C4 is 256 hertz. Okay, so what is resonance? Okay, resonance is and you gotta say it with a rolled R, right? So resonance is a property that when it's how very small agitations induce large vibrations at the natural frequency. Right, so basically, in order to get this swinging at its natural frequency, right, I had to exert a pretty large force, right? It's around like 5 newtons. Pa! Right, and now it's going this way. Ba, 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 right? But what if I told you I could do the same thing, but barely exerting any force at all, right? With a force that big. What are you talking about? Well, just wait, just wait. Right? What was the trick to making it actually vibrate at its natural frequency? If my super small agitations are at the natural frequency, then it'll cause the object to vibrate at its natural frequency, even if it's a super small agitation, right? And only if that super small agitation was at the natural frequency. Look what happens if my agitations are not at the natural frequency. So what's the natural frequency to begin with? Let's measure it. Oh, sorry. Let's measure this. Boop, 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 right? So if I do that, boop, 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 right? It starts resonating, right? But if I do it at another one, like boop, like boop, 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 right? Boop, 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 boop. Nothing's happening, right? But I have to go boop, 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 right? And then because my agitations sync up with the natural frequency, then oh, did that hurt when I hit the keys? Really? Is it because of my mic? I'm really sorry. I'm so sorry. That's my fault, isn't it? Yeah, and if you are wearing headphones, I'm not hating on you for wearing headphones, right? Some people like have different living situations where they have to wear headphones, right, to not disturb other people. Wait, Isabel, why is it so painful? What are you talking about? You better clarify yourself. Isabel, you gotta clarify yourself. Like, what's so painful about it? Or you get a -1, okay? I'm gonna enter grades this weekend for the past month. I'm entering them every month. Yeah, so here, that's exactly what happens in like the very classic example where like I have a glass, this is its natural frequency, and if I sing really loud, right, I can cause, without even touching it, I can cause the glass to resonate at its natural frequency as long as my own voice kind of as long as my own sound waves that I create match its natural frequency. So, right? So if I sing super loud into this glass, right? Right? Then the glass itself will start resonating, even without me agitating it, right? It'll start resonating. And and that's the whole point of resonance, right? A very small agitation can induce large vibrations and cause this to thing. So what would happen if a large agitation is at the natural frequency? It'll create a super big resonant effect, and the glass will start vibrating so much that it'll crack, right? Because the material isn't meant to be bendy like that, right? So I'm going to try my best to do that. I don't even know where the mics are located on my laptop, but I'm just going to... Do you guys hear that? Did you hear that? Nothing? Okay, all right, I'll try it again. So you guys should hear nothing right now, right? Nothing, nothing, nothing. And now look. Oh! Oh! Oh yeah, I hear it. I totally hear it. So, oh! Oh! It's very faint, and I wish there's a better way for me to show you. Yeah, right. It's super faint, right? But what you did notice was that it's playing the exact same note that I sang, right? Because like my voice at that frequency matched the natural frequency of the glass, and that caused the glass to resonate. Okay, it's extremely hard to do. It's like I can hear it clear as day, right? And this is like one thing that makes me really sad about not being in class with you guys, but you know, there you go. Okay. Yeah, that's basically what resonance is. If you guys want to look at some really extreme examples of resonance, right? I would highly recommend uh, I would highly recommend looking up a video about the Tacoma Narrows Bridge. Dissonance has nothing to do with resonance. Dissonance is like a musical term that basically describes anything that sounds bad, right? So dissonance is not the opposite of resonance. Dissonance is the same, dissonance refers to like a musical interval, like a half step, or like a chromatic half step that does not sound good when they're played next to each other. Alexi, that's like a really great question, right? So why does an A sound so nice with a C sharp and sound so bad with a B flat, which is a half step away? That has to just deal with like how our brains kind of like receive the information of the notes, right? So exactly, that means it's really possible for like other animals to hear what we think is something dissonant and not sounding too good to actually sound pretty good, right? So, but there is a mathematical relationship. So we can like just based on like what we know about human beings and like what we know to be sound good, you can kind of like predict what humans will sound good just based on the mathematical relationships between all the frequencies and stuff, right? But I would look up the Tacoma Narrows Bridge. That's an example of a very large object resonating at its natural frequency. That bridge actually did this. It actually did this, right? And it's a concrete bridge, and it wiggled so much it broke. Why did it wiggle? Because it was so windy. The wind actually agitated it enough to where it could start vibrating with a pretty significant amplitude. Fortunately, it was strong enough to withstand it for like up to an hour. So everyone evacuated the bridge. But what you do see is like you see abandoned cars on the bridge because people just left their cars there, and you see like the cars like going up and down, and the cars were lost too, right? Right, they fell in the water and stuff. But that's an example of like something like really large resonating. For most strings, right? So here's a key point that should go in your notes. For most just like normal strings, the resonant frequency, the natural frequency that it will vibrate at, corresponds to the fundamental frequency of the standing wave created in the string, right? So the natural frequency of a string is the fundamental frequency, is the frequency of the fundamental standing wave. How do I calculate that? Well, I know that the wavelength of the fundamental is 2 times the length of the string, right? We went over that a long time ago. For those of you who want to review, right, that's my fundamental, right? Anytime I hit a string, it's basically going to oscillate from this position to this position. Wah, 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 right? And it's vibrating at it's making a standing wave, right? And it's making the fundamental standing wave, more importantly, okay? That happens to be one of the many sheets I've kept, right? The others, I'm basically making a giant pipe organ. This is a monument to our remote learning time together. Wow, look at all of those, look at all those. That's less than half of all the sheets that we've gone through, right? I've thrown away most of them. Anyways, so that's, and it's gonna be the fundamental standing wave. How do I find that frequency? Well, if you know the V is lambda times frequency, so this is 2L times the frequency, that's gonna be your natural frequency, right? Well, how do I solve for that? You're gonna need to know the speed of the wave that travels in that string. And that's going to depend on the properties of the string, right? For my students who play guitar or violin, the actual formula for the velocity is the square root of tension, the tension in the string, all over the linear mass density, right? So what you'll find is the thicker strings, right, have more mass per unit length, so they'll have a smaller velocity and they'll have a lower frequency, right? That's why the thicker strings play a lower note when you pluck it, even though it has the same wavelength as another string, right? The other way to change the velocity is to tighten the string, right? So when I tighten the tension, the speed increases, and without even changing the length, it changes the frequency at which it goes, okay? We're gonna go over that in a lot more detail, okay, next week. So next week is gonna be all about music, so get really pumped. And we're gonna start off, I'm gonna show you a video. You're gonna have another reflect. So it's like, these aren't really assignments, they're just kind of guided notes with which to like watch the videos with. So I'm gonna give you another video of a lady who is one of like 4 in the world who can sing more than 1 note at a time, which is insane. Ever since I've seen her videos, like I understand the theory of what she does, but to put it into practice, I still have no idea how she does it, right? Yeah, and that's gonna be really cool. So I'd like for you guys to watch that and fill out the worksheet for that while we go, and to have that done by Monday. Because if you don't, you're gonna be pretty lost on Monday, all right? Yeah, so get pumped for that. All right, we're gonna have open office hours tomorrow, so you guys can talk about anything, and I'll see you. Okay. Oh, this is different than throat singing. So throat singing, you basically like make your throat, like you growl at a specific frequency and then you sing. So like you're growling and you're singing at the same time. What this woman is doing is actually singing two notes at the same time. And she can sing like two really high notes at the same time, which the Mongolian throat singers like don't really do, right? Because they're basically like singing a mid-range note above like a really low fundamental note. This woman can pick any two notes she really wants and sing them anywhere, like a real instrument, right? It's kind of crazy. Okay, yeah, so be prepared. I'm gonna send that video either today or tomorrow. I just want you guys to chill. You'll have the whole weekend to watch it and like kind of try and explain what's going on. And then we're gonna go over that Monday and then talk more about music. And then the week after that, we're gonna start light waves. Whoa, okay. So have a great day. Don't stress out about your APs too much and be respectful on the internet, okay? Have a great day.